somehow
Yes.
connection was lost.
Okay. Can you share again? Yeah.
Yes, I'm sharing.
Okay. Are you ready?
Yes.
Is it okay? Okay. Let's start. Hi everyone. Today we will begin the third lecture of the Kantaro Ohmori. Let's welcome the speaker.
Thank you. So let's start today's lecture by again recapitulating the last day. And so what we have been doing, we have been talking a lot about projective representations. So we thought about Z2 times Z2 subgroup of SO3 generated by the pi rotations along either of XYZ axis. And this action on the brachiosphere. Okay, and we saw that there's a projective phase. Okay, and I mean, and this was non-trivial, not removable. And then we talked about this particle on S1, and where with magnetic flux through it. Okay. And then so there again, this model have U1 shift symmetry and semi-direct product with Z2 flip. So the model was we have a ring or socket. We have the magnetic flux, and when this is the half of the flux from the Dirac monopole. So in the variable we are using the theta equals to pi. Theta equals to pi. Then this thing has non-trivial project phase. And also the subgroup, the Z2 times Z2 subgroup, also have the non-trivial projective phase. So this is U1 shift, just the rotation, and the flip is a mirror symmetry. See, this is it. Okay. So this Z2 is broken away from theta equals to 0 or pi, and at theta equals 0, this Z2 is of course preserved, but there is nothing particular happens, and there's no non-trivial projective phase. When theta equals to pi, then this Z2 have a projective phase. Okay. Yeah. So well, I didn't say this, but this. So at theta equals to pi. So well, roughly speaking, this Z2 flip sense the theta to minus theta. And when theta equals to pi, then this pi goes to minus pi. But as we saw that there's a 2 pi periodicity in the parameter theta, so this is equivalent to the model with the theta equals to pi. But to essentially for the Z2 to be preserved, make the theta equals to pi invariant, we have to invoke this 2 pi periodicity, and that's where this something non-trivial happens, in a sense. Okay. And okay, and then therefore there is a twofold degeneracy. And in the energy spectrum, at theta equals 2 pi, every energy eigenstate has twofold degeneracy. And this twofold degeneracy is not is robust or protected, or protected against the deformation of the system, preserving deformations that preserves Z2 times Z2.
Excuse me.
Yes.
Could you remind me what is the definition of triviality or non-triviality?
Okay. So
Please?
I'm soon formalize. So I will soon answer it. But
okay.
yeah. Yes. In a more abstract language. Yeah. Well. Yes. Roughly speaking, it's just you cannot remove the projective phase by redefining the unitaries. But I'll be precise in that soon. Yeah. There's also
I'm still wondering or have some difficulty in figuring out what kind of topology it is measuring. Your cohomology represented by this projective phase.
So well, so one, I might answer to your question last day. Well, half answer, I can't fully answer, but in the flat space, just a particle on the flat space without any potential and with a uniform background, uniform magnetic flux, then so there is a magnetic translation operators that the some kind of modified translation, and so that's so the particle on R2 with flux, and this have magnetic translations. But that's like Tx and Ty, but like this translation does not commute. It's like this. So this is like, yeah, so the unitary is the exponentiation. u x minus 2 to the t x y. So in a sense, this is R2. So this is projective phase for R2. And yeah, so there is a projective phase. I do not really understand the relationship between this projective phase and the infinite Landau degeneracy though, but at least there's a projective phase for coming from the translations, to magnetic translations. Okay, so that's one answer. Yeah, and for the answer for your question today, so what is the topology? Well, yeah, so that's like in this case, the brochosphere have some topology. It's if you think about projective space, then it involves the topology. So that's very one source of the topology, and that's a kind of thing. Yeah, I'm going to introduce a group homology by very algebraic way, and you might want to know the more geometric realization of the same cohomology group, and that is possible, but you need some infinite dimensional space. That's the topic of algebraic topology. Let me keep move on and formalize. I mean, talk about the general stuff, and then you might ask again. So today, so let me first formalize that we have what we have seen in the examples. Okay, so for that, I talk about the second group cohomology. Okay, so now let's assume abstractly that we have some group that acting on the projective Hilbert space. Okay, so we have for each element G, we have TG acting on pH. Just write this way, pH to pH. Okay, and also this symmetry transformation is just respects the group multiplication law. So TG1, TG2 equals to TG1, G2. Okay. Then by the Wigner's theorem, there's a corresponding U of G acting on H to H. This is unitary. Well, let's assume this is unitary. And it can be anti-unitary, but let's assume to be for simplicity, let's assume this is unitary. And okay, so then by Wigner's theorem, this is unique up to the overall phase rotation. Okay, so what this equality means that for among these unitaries, we have multiplication law. and is it alpha G1, G2? Okay, and this is the projective phase. Now, okay, so there was a question in day first that but how about the associativity? Okay, so you are matrices, and matrices have satisfies associativity. So you know U G1, U G2. First multiply this and then multiply U G3 equals to U G1 multiplies U G2 U G3. Okay. But then you plug this to this trivial equation. And what you find is the constraint. So constraint on alpha, that is, let me write this way, alpha G1, G2, and minus alpha G1, G2, G3, plus alpha G1, G2, G3, plus alpha G2, G3, and goes to 0. Okay. So this comes from this part. This comes from this multiplication. This comes from this multiplication, and this comes from this multiplication. Okay. Okay. So let me call this thing. Let me define this thing to be delta 3 of alpha G1, G2, G3. Okay. So alpha is not arbitrary because of the associativity of matrices, but under the constraint of this type. Okay. Good. And okay. But then, well, this is mod 2 pi, by the way. Then also not all alpha are interesting, because we can redefine each U of G to replace this to modify it by some phase depending on the group element. Okay. So if you do that, then this alpha G1, G2 so becomes alpha G1, G2 and okay, plus beta G1, G2 minus beta G1 minus beta G2. And So far, so good. Yeah. This is also clear that the definition of alpha, if you do this, then here you get additional. If you replace this by this, then yeah, well, if you do the active action, then you get this factor here, and then this factor this side. So again, this is mod 2 pi, and I call this to be minus. The negative sign is just a convention, negative of delta 2 beta G1, G2. So alpha, so here alpha is the map from the product of the same group to R mod 2 pi Z, because alpha is meaningful only mod 2 pi, because it's a phase. Okay, and then this beta, it gives like G1 okay, and so let me define the cochain. So n let me n cochain Cn of G varied in R to the Z is just a set of maps from G to N R to by Z. Then alpha is a 2 cochain. I'm writing the same thing. Then beta is 1 cochain. Okay. Further, these deltas, I define delta 3 and delta 2. The delta 2 and 3 respectively sends C1 and 2 of G. I'm suppressing this value. Okay, it's a in this context, so it's always U1 to C2, 3 of G. Okay. So I just introduced the notations. This is a map. Delta 2 and 3 defined here and there is a map from the 1 or 2 space of 1 or 2 cochain to the space of 2 or 3 cochains. Okay. So then alpha is, okay. So the associativity means told us that this one, because the delta 3 of alpha equals 0, and this is called the co-cycle condition. And we call Z2 of G be the set of cocycles, namely the alpha in C2 of G, delta 3 alpha equals 0. Okay. So the actual projective phase is always the element of is a cocycle. In other words, an element of this group. And also the interesting alpha is such that there is no beta in one cochain beta, such that alpha is delta 2 of beta. Okay. Okay, so this page I just introduced the notations and rewrote this and that. Okay, so this motivates us to define, answer. And then the one important thing is important fact. Is that delta 2 composed with delta 3. Delta 2 sends one cochain to two cochain, then delta 3 sends two cochain to three cochain. So this sends one cochain to three cochain, but this is 0. Okay.
Question?
Yes.
Can you give expression for this delta? Maybe it's called the co-derivative, something like that.
It's derivative. Yes. It's
Yeah. So
yes,
can you give explicit expression for delta when it acts on general Cn instead of just C3 or C2? So here you have gave
yeah. So well, yeah, I don't have a motivation. I haven't explained the motivation to define it for the general N, but let me just, well, what I do here is just open the Wikipedia and copy it. I don't remember in my head, but
also another question is that what will be the delta 1 or delta 0? I mean, the other N.
Okay. So delta, let me see. Delta 1, that means 0 cochain, and 0 cochain. Let me open. I don't trust my brain. So of course there is a general stuff. So okay, let me write here. So general delta n. There's a delta n of phi g1 gn plus 1 equals to, so I assume that the action is trivial. So g phi of g2 gn plus 1 and I equals to 1 to n minus 1 I and phi g1 g I minus 1, yeah, then g I g. I recommend you to really open the Wikipedia. That will be more clear because it's very hard to read. Sorry for my bad handwriting. G1, Gn. So sorry. So to be clear, this is a multiply group element. These are different the group elements inserted for different slots of phi, but this is multiplied group element. So I hope this is comprehensible marginally. Okay, so this is the general formula. Okay, so let's see that what is the delta 1 and delta 1 of phi of G. Okay, and maybe sorry. This is definition delta n plus 1. And so the first term doesn't exist. Yeah. I think second term also, I mean, phi is some, in this case, phi is 0 cotangent, so it's some just element of the value. Okay, so what? So it's minus, yeah, I think it's minus phi. That's one cotangent. Independent of the element. No, right? Or is it 0? So this the intermediate thing is 1, but n is 0, so there's no, yeah. So yeah, I think that's, yeah.
Okay.
And yes. So that's one. And yeah, so this is general definition. Yes, yes, of course, yeah. So you can extend this to the higher order. Okay.
Okay,
And
okay. I understand. Yeah.
Thanks. Yeah. Yeah, the general formula is not very simple. Yeah, it's a bit complicated. Yeah. And hopefully I can talk about the third cohomology the next week. I'm not sure I can do the ultra. And in the context of the anomaly. And okay, so it's a good exercise. It's very, for at least for this. Well, if you want for general degree, but for this degree, just exercise to check this. This equation, and because of this equation, this is called the derivative. So C1, C2, C3. Okay, and if you compose the two, it's 0. Okay, and this is a setting that you can you do the cohomology.
Yes.
If you have heard about it. So and that's precisely what we want, because alpha, the projective phase always satisfies this, and then also we are not interested in alphas that can be removed by shifting by delta 2 beta. Okay, so the classification of interesting or non-trivial, interesting or non-trivial alpha, I mean projective phase, is given by cohomology. In this case, the second cohomology of the group. Let me reinstate this and define by the quotient. Okay. And this quotient thing is the quotient of among the groups. Yeah, so this condition ensures that the I didn't define the B. So it's a B. Here the B is the delta 2 betas in where beta is in C1 G. There's a definition of B, and this is inside because it's delta 2 delta 3 equals 0. So this is inside Z2 of G. Okay. So this is the definition of cohomology, group cohomology. Okay, so this is our algebraic definition of group cohomology. And that naturally arises from the physics of projective phase.
Question?
Yes.
So then, can you construct something similar, like a long exact sequence of standard cohomology in this case too?
Yes.
I mean, as far as I know, that was the only method we can compute cohomology groups. As far as I know, usually that was the usual technique.
So there are various techniques to compute that I cannot explain. The
Okay,
yeah, the
maybe
central one is the Seres spectral sequence. That is the main techniques. But yes, there is a relative version of this group cohomology, and there is a long exact sequence.
Okay.
Also there's a long exact sequence coming from the exact sequence of groups, abelian groups. Yeah, so that's that also. Yeah, so there are various kind of things.
Can you give one? Okay, thank you. Can you give you one explicit example for the computation of H2, or
so
maybe
okay.
based on our examples studied so far?
So yeah, Z2 times Z2. Well, let me see. What is can I do that on the fly? Well, let me first just a list of known results and the second cohomology. Second cohomology is quite easy. Second, it's like Z2. So Z2 times Z2 valued in. So I suppressing this part, okay? And this is Z2. This is what we have been seeing. And H2 of SO3. This is also Z2. Okay. And this is basically coming from the inclusion or the other way down. So. Okay. Also, what did I write? The cohomology. So group cohomology. Oh yeah, I didn't know. Yeah. So, well, this might be too trivial. This is 0, and so let me see. Well, so alpha, but if the value is restricted to Z2, then it's Z2. And okay. So that would be these examples. Okay, so let me see. Well, this thing, these two is easy to determine because there is only one non-trivial element. Okay, so let me see it. So, well, the small fact is that you can always set that the alpha of G1 to G1, G2 equals to, well, alpha of this one is identity of the group. G2 equals to alpha G1, 1 equals to 0. Okay, so this is by choosing, by shift choosing appropriate beta. Okay. Maybe just okay. This is small fact. Let me assume this. So, well, this physically this means that if one of you can always choose the unitary for the trivial symmetry transformation is the identity, and if U is identity, then you never have this projective case. Okay. Okay, so that's from the just definition. It's not very obvious, but it's a small fact. Okay, then okay, so then when group is Z2, so when G is Z2, the only thing we have to care about is the alpha G alpha of let me call this is 1 and a square equals to 1. Okay, then only thing because of this small fact, then let me assume this, then the only thing we care about is alpha a of a, and this is like inside inside R over 2 by Z or Z2, depending on the choice of here. I mean this. And then beta of delta beta of a okay, so from the definition, delta 2 is this, so it's beta of, let's see, a squared equals to 1. This is negative. So is beta a equals to beta a minus beta 1. Okay, but if beta 1 is non-zero, then that destroys this. Okay, so we set beta 1 equals to 0. Okay, to preserve this condition. Okay, don't do anything with the identity. Okay, so then this is like 2 times beta A. Okay, so for the H2 of Z2 of over 2 pi Z, we pick that beta A is half of beta alpha AA, then alpha equals to delta 2 beta. Okay, so this is trivial for any alpha AA. Okay, so H2 is Z2 valued in U1 is 0. However, if you ever care about the Z2 value cohomology, actually you're talking about the time reversal times Z2 unitary symmetry, then that's the case. So sometimes you do care about Z2 valued cohomology, and in that case, 2, so 2 is 0 in Z2. So in other words, you cannot divide an element of Z2 by 2. Okay, so there's no beta such that. So if alpha AA is 1 in Z2, then no beta such that alpha equals delta to beta, and therefore Z2 H2 of Z2 valued in Z2 is Z2 generated by this non-trivial alpha. So this is example. The case you can explicitly compute. Any question? I think you can do you can do the similar thing for this case and see that there is a non-trivial element, non-trivial cocycle or non-trivial projective phase in the case of Z2 times Z2. Okay.
Thank you.
Yeah. Well, yeah. Actually, when group is continuous, there is a subtle thing. I believe at the degree 2, it's okay to write it this way. Yeah, sure. Okay. And any question about the group cohomology? So this is how to classify the possible projective phase when you have some symmetry group acting on projective space. Well, this is a classification of anomaly in more QFT language. Okay, so if everyone is happy, then let me talk about some condensed matter stuff. Okay, so here the anomalous symmetry. And SPT. Okay. So the importance of the group cohomology, well, was of course known by Wigner, but in essence, but
One small question.
yes, please.
So just going back to group homology.
Yeah.
Suppose that your group G
Yes.
is a direct product of say G1, G2, or quotient group G1 by G2. Then do you have some general theorem for such cases?
So when the value is U1, yeah, so that's universal coefficient theorem.
Yes, so that's what I'm thinking of. So I'm just wondering whether such kind of thing happens for group cohomology case. So,
well, okay. So the group cohomology is, well, here I define it in the algebraic way, right? But it's also so this is group cohomology. Maybe. So group cohomology of G varied in some abelian group is equals to the algebraic topology. Well, algebraic topology. Some cohomology of some particular topological space. This is classifying space. Varied in A. So there's some particular infinite dimensional. So this is infinite dimensional. Space, topological space, CW complex. And so here, like, simply show or cellular cohomology. So the one I define in algebraic terms is actually this can be realized geometrically using some infinite dimensional topological space. Okay, so in this sense, what do you know about the cohomology on the topological space can be applied.
Algebraic geometry, algebraic topology.
Yeah. The whole of algebraic topology is applicable. Yes. Yeah. All the tool set is applicable. Yeah.
Okay. Thank you.
Yes. And yeah. So this is Well. So yeah. This is a cute topic, of course, very cute. And the classifying space, like, so suddenly you need to think about some infinite dimensional topological space, like B of Z2 is RP infinity, B of U1 is CP infinity, and blah blah. Yeah, B of Zn is some infinite dimensional lens space, and B of SUN is some infinite dimensional Grassmannians. Anyway, those are the So and don't be confused that I put that note. Don't be confused that this and this is not equals, of course, to the geometric group cohomology of the group. Okay, if this G is Lie group, you can regard that as a manifold and think about some drum cohomology or something. And that's not the same as this group cohomology.
Okay.
Rather it's that of this some humongous space.
Oh, thank you. Very interesting. Yeah.
Okay, so let me the rest of today I talk about some so far I've been only talking about some small examples and now let me talk about more big picture of what's going on and also the relationship to condensed matter physics, some topics in the condensed matter physics. And so the importance of the group cohomology, including the higher order ones, H3, H4, were noticed by condensed matter physicists. So by the paper 3 of the note, so there's a Chen and Gu, Liu, and Wen. Wen is a famous Xiaogang Wen. And it appears in archive in 11 on PRB on 13th. Anyway, this is the I found is symmetry-protected topological fields. So before defining what the symmetry-protected topological fields is, let me explain the importance of this this thing. And so in HepTH perspective, we abbreviate this by SPT, and SPT is a precise version of inflow action. Here, the inflow action is by the Callan and Harvey. So Callan Harvey when was 85. Okay. So inflow action is like for perturbative anomalies. So the perturbative anomaly, like triangle anomaly, then there's a say 4D. Okay, then what Callan and Harvey taught us is that it's better to think as of this 4D system as a boundary of one 5D system, and in the bulk of the 5D system, we have effective action like AFF, where F is the A is U1 background. Okay, and then this cancels. So then if you put the effective action on the 5D, then this cancels the anomalous transformation law. So that's this one. Now, okay, so of course that has been known for a while, but from 85, but this SPT enabled us to generalize this kind of inflow treatment into other cases. okay, and including the discrete symmetry and global anomalies. Okay. So where this inflow action is more subtle, that you cannot write it down as using some continuous background field. First of all, the symmetry is discrete, then the background is also discrete, and you need to know how to treat these background fields. Okay? And that generalization, I think the generalization of this inflow stuff into the discrete case was not known, I think, before this SPT, but then people in HepTH, after the appearance of this seminal work in condensed matter physics, then people in HepTH side also notice the relevance of this SPT in this context and relate them. Okay, so generally, we believe the hypothesis 2.1 in my note, the following hypothesis. I think this is not proven in any sense. That D plus one dimensional QFT with anomaly symmetry G, and let's assume that this is global. And here I assume that without pure gravity anomaly. For the pure gravity anomaly, you need an improvement, but let me not talk about it and move. Okay. Can be realized as a boundary of D plus one dimensional SPT. Okay. So instead of the inflow action of this Chern-Simons type, we regard the general SPT is what replaces the Chern-Simons action in general setting. Okay, so this is the hypothesis that we believe. Okay. Again, this is not proven, I think, in any meaning. So anyway. Okay. So then what is SPT? And here I explained the SPT by the definition of Wen and his collaborators. There's a subtle different version of it, but I put some footnote about it. So okay, now okay, so this is a property of a state, the property of a state typically taken to be the ground state. Okay, and good. And first I define the short range entangled. Called abbreviated as SRE. That us. Okay. Okay, so here I'm working on the lattice system. So we have some lattice. And okay. And so each site we have local Hilbert space HI, some space of spins, say. So the total Hilbert space is the tensor product of the local Hilbert space. Okay. As we are working on the lattice, then so a state, the single state in this total Hilbert space is short range entangled. If so, this is a definition. All right. So if you can make turn this state into a tensor product state, okay, by the following operation, where the tensor product state is like pick. This is like tensor of Si, well, maybe I will use S. Let me see. This, phi I, psi I, where each psi I is inside Hi. A general state has an entanglement between the sites, so the general state is not a tensor product state. Okay. Okay. Then so this a state is called short range entangled if you can make it into a tensor product state by first add the degrees of freedom. So you enlarge Hi to Hi enlarged. So this is like you put additional degrees of freedom if you want, if you need. Then do some local unitary. Local unitary I have Ui, and Ui acts on the Hi enlarged. Okay. So this is not arbitrary unitary. So each unitary should act on just a site, a single site. After adding some decoupled degrees of freedom. Okay. So this is a definition. We will soon see the example of such. But this is a definition of short range entangled. Okay. Then we also define G short range entangled. I mean, so here we assume that the G acts on the Hi, or like maybe P of Hi, and each site, and also psi is invariant under G-action. Then psi is G invariant, G SRE, that if the above UI, so in the definition of short range entangle, this UI preserves G. Okay. And you can let G also acts on this additional thing. But this is just it. If you can make the state into the tensor product state while respecting the symmetry, then it's called a G short range entangled. And then finally the definition of SPT is that so G invariant state psi is in SPT if psi is short range entangled, but not G short range entangled. Okay. So you can untangle all the entanglements by local unitary, but not the way respecting the G symmetry. That's called the symmetry-protected topological phase. Okay. So this has been just notations, I mean concepts. Okay. And let's see some one example of SPT. And so from if we believe this hypothesis, in particular when D equals to 0, there should be a SPT and whose boundary possesses this projective representation. Okay. There has to be some inflow in 2D that inflows this anomaly onto the 0+1 dimensional space. Okay, so let us construct that for the case of Z2 times Z2's projective phase. Okay, so here the example for the SO3, the same. So the 1+1D SO3 SPT. Okay, so to construct this SO3 SPT, so first we have to define this one. This is 1+1D lattice or spin chain. So we have one-dimensional lattice. Okay, and site. And for each site, we put some Hilbert space, and here we take the single site Hilbert space is C2 tensor C2, so 2 qubits. Okay, and let me call the first one is A qubit, and the second one is B qubit. Okay. I just simply put the C4, but I factor it into the tensor product of 2 qubits. Okay. Okay, so actually I have for each site. So for each site we have A qubit and B qubit. Okay. So let me write for each. B qubit. Okay, so it's actually a bipartite system. And this single set is, this is HI. Okay. Okay, so this is the Hilbert space I pick. Okay. Then to define this a state, I first prepare a state Si to be this one. So up state in in I and B. So this Si is, let me write first. So up state in B qubit of I state, and down of A qubit in I plus 1, and negative 1 IB up state I plus 1A. Okay. So this is basically a singlet. Okay, but this entangles ice state at the ice Hilbert space to and I plus 1 Hilbert space. Okay, so this is not inside the HI, but this is inside IB. Then so A I plus 1. Okay, so this is not the local state. It's not the local state. Okay. And rather this Si have an entanglement between this A qubit at I plus 1 and B qubit. Oh, sorry. Okay. Sorry. To be consistent with my lecture note, I flipped the A and B in the figure. So, and then it's Si schematically, it looks like this. So this is Si. Okay, means so this is the Si. Okay, that introduces the entanglement between B qubit at I site and A qubit at the I plus I site. Okay. Then I pick psi is just a tensor product of these Si states. Okay, so again, I will write. Yeah, I can copy and paste. Maybe I do this one. Okay, so this is psi. Okay. So the point is that there's entanglement here and there. Okay. So I site is entangled with I plus 1 site because of this effect. Okay. And yeah, but it's short range because the entanglement is just cut off here. So it's only entangled with to the next one and not far away.
Sorry,
Yes.
I want to ask one question. What is the local state here?
So local state is a state inside defined like psi I in hi.
Okay,
Insist my definition of local Hilbert space is this. Okay,
so
the same.
so you say it's not a local state because you use hi tensor product hi plus one.
Yes, yes.
Okay.
I introduced the
Okay. So you mean that SI is not a local state?
it's not
Okay.
yeah.
Okay. And then I want to ask the next question. How do you define HI8 here?
So HIA and so I pick HI.
No, not
Yeah.
A8 because in the previous slides, I think you defined the HI8 ADD.
Oh yeah. Okay, so here
How do you define
at this stage I'm only explaining this choice.
Oh, okay.
Then
So
to do this one, you need to be clever to find this operation to make this state. So this state is entangled. So to make this to make trivial, make it a tensor product state, you have to add some degrees of freedom, and that you can choose. You can choose, but I mean for safe, you can choose very humongous state Hilbert
yeah.
space.
So it is one of my confusion because you can choose HI8.
Yeah.
So does it mean that the show SRE is very artificial?
Yeah, it's kind of artificial. Yeah.
Okay.
I mean
Okay. So precisely, you should just first define what is HI8. Then you can say you can define what is SRE, and then you can say what is SPT.
No. The definition of SPT or SRE here is that given a state, okay, you try for whatever choice.
Okay.
So HI add is not fixed. Okay, in this definition, you can take any Hilbert space, maybe separable, just a separable Hilbert space. So maybe you put the infinite dimensional one. Okay, and then do whatever unitary. Okay, and for any choice, if you succeed to turn this psi into a tensor product state in this enlarged HI, okay, then that's a short range entangled. Okay? So that's the definition.
Okay.
Okay. But here in this example, you can. So this is the precise definition. I mean, I want to show that there is a precise definition. But here, the more intuitively, I'm not going to prove that this is short range entangled according to the definition. Rather, I just say that by words, the entanglement is short range. The entanglement structure of this state is short range, and that's what it want to mean. The definition want to mean. Yeah, that's a bit non-trivial. But yes. Okay.
Thank you.
Okay. So this is. I mean, by picture, it's short range entangled. And okay, and I take the action. So I want to pick the SO3 action. Okay, and that has to be on site. So so for G in SO3, then I define the symmetry transformation on this that is Hilbert space as this one. Okay, just for a qubit it acts on both a qubit and b qubit separately. But for a qubit, it's acts on G, then on B qubit, it's as its inverse. Okay, that's my action, and this preserves, and this is so in this form, it's obvious that this is local. Okay, because it's the product of the one acting on each side. Okay, but also this is equals to I and T B I B. G inverse I B T G I plus 1A. Okay, I just shifted the product structure into this. Okay, and this form is, in this form, it's manifest that this preserves this psi, which was defined as the okay, because SI, this is singlet. Okay, that's my choice. Okay, this is singlet, so it's invariant under the action of S. Okay. Then, well, I'm a bit afraid to should this be plus? Because so should this be plus? Because I put the minus. Well, let me check later. I don't have time. And so this preserves psi. Maybe I made a mistake about the sign. Okay. So then I want to claim that this is SPT rather than prove it by definition. So the detail can be found in the nice paper by this paper, not the Shagan-Wens, but this one, the Prakash, Juven Wan, and Wei. But let's see that this realizes this hypothesis. Okay, that on the boundary there has to be some 0 plus 1 dimensional system that magically appears. Okay, so yeah, so this picture is defined on the infinite lattice, but let us chop and chop it somewhere, say the 0. Okay, here I erase and okay. So what happens? What happens is that this part doesn't change, or you can just put the same structure, but this qubit doesn't have its pair to make an entanglement. Okay, so there's an open qubit, a qubit at on the open chain, then at the boundary. Okay, and this one, I should stop here. So, okay, and on this orphan qubit, it's the SO3 acts as this TG of 0A. This is the one action on single qubit, of course. And therefore, there's a, as we have seen, that the project phase. So there's a twofold degeneracy. So this gives you the, if this psi is realized as some local Hamiltonian on the spin chain, then this if there's a boundary, then this orphan A qubit gives you the degeneracy on at boundary. Okay. And that precisely the zero corresponding dimensional system that that have anomalous SO3. Okay, so this is an example of, okay, so that's the manifestation of the SPT. Okay. So the property of SPT, if you assume this hypothesis, is that when you cut the system, then on boundary you have some non-trivial degrees of freedom, and that's what we have seen. Okay, and you can easily generalize this construction to the general projective representation that you can, yeah, as wrote in the note, you can easily cook up some SPT phase in 1+1 dimensions for any group G, so that on its boundary you get the boundary degrees of freedom that have the particular projective representation. In just generalizing this example. Okay, so that's the and yeah, so this correspondence between the SPT and anomaly inflow and the boundary degrees of freedom and anomalous QFT is the very central theme of in the research. Okay, so yeah, I'm happy to said that, and so the time is up. So I stop here and take questions.
Yeah, thank you very much for the very nice lecture. Please ask a question. Sejin?
Yes, this is yes.
Sejin, unmute your mic. I saw some people raise your hand.
Oh yeah,
So-
just unmute your mic and.
Oh no, I just clapped the.
Oh, I see.
Not the question. I just clapped.
Thanks.
For the wonderful lecture.
Thanks for clapping. Yes.
Can I ask a question?
Sure. Yes.
So for the last part, how did you see that this, qubit at the edge is in the projective representation?
Well, we've seen that qubit is acted by SO3 as a projective representation. That's the brachiosphere is naturally acted by SO3, but cannot be realized.
So
Yes,
I see. So a single qubit is always in the projective
yes,
representation.
yes,
Okay.
yes.
I have another question. So you mentioned this classification of projective phase And
Like
so
group cohomology, yes.
yeah, so yes. So if you consider the perturbative anomaly, then that can be classified, I mean, for example, by the anomaly polynomials, right?
Good,
I mean,
good. Yes,
in
yes.
sixth dimension. So what is the relation between those two?
Good question, and that's actually not very easy. So the classification, well, the anomaly in, I mean, then we got the bosonic anomaly, actually, but roughly speaking, not very precise, but roughly speaking, anomaly in D plus 1D is like H classified by H D plus 1 G and U1 valued R over 2 by Z. However, for discrete Z, for discrete G, but when G is continuous, then above algebraic definition breaks down. It's not precise. So you have to deal with the you have to carefully deal with the topology of this continuous group. When you are talking about some U1 or SUN, it's not just a group structure, but you put the continuous background, right? You think you can put the continuous magnetic field or electric field, and that that deal with the topology. So actually for continuous group there's complication. So from this perspective, the discrete group is easier and the continuous group is more tedious. And so yeah. So here for continuous case, you have to deal with the shift cohomology, blah blah. So there's some refined version of what I have described to deal with the continuous part. But roughly yes, roughly you just think about the higher dimension and dimensional cohomology, but with a bit more careful definition. Yeah, you can also use this side. So this equality is only for G discrete, and you can also use this side for continuous group. Then that you just generalize. Thanks for the question.
So for continuous group, I mean, the right hand side, I mean, it is going to characterize the anomaly.
Yeah.
Okay, so you have to consider the, I mean, cohomology of infinite dimensional space.
Yes. Well, am I right? I'm a bit confused. Yeah. But you can use this algebraic definition because there's some.
And can you relate an element of this right hand side with this anomaly polynomial?
Oh yes. That's like a Chern-Simon more precisely. More precisely, it's a Chern-Simon's thing, but yes. Yeah.
Okay. Okay, thank you.
Yeah, for the discrete group, there's something called the Digraph-Witten action. That's the analog of Chern-Simon action for the continuous group symmetry. So that's also another relationship. Yeah.
Any other question? If not, let's thanks speaker again.
Thanks.